I was a little surprised to notice how this math equation solver, it's a internet resource for math, but it choked on this equation. None of these are solutions, and I don't have any idea how it did it, other than it converted this to a fifth degree polynomial and then tried to do the rational zeros theorem. But none of these are solutions, which is kind of puzzling for an established resource on the internet. Now I'm going to show you an approach here. By the way, I didn't tell the equation solver that there is an integer solution, which is a tremendous amount of information. So in all due fairness, maybe, I don't know if this is a hard problem, but if you tell somebody that there is an integer solution, that changes things immensely. Now, one thing to notice that really makes life fairly easy, believe it or not, is that this piece right here certainly factors into x plus 1 times x plus 3. And this denominator over here is x plus 2 times x plus 4. Now, that turns out to be immensely useful. This is just the simple algebra. You can just juxtapose these four linear factors together. And notice that you have consecutive integers in the denominator. And the numerator turns out to be irreducible, which I guess is important. And 13, it doesn't have any factors in common with 5040. And it doesn't take too long to write down the prime factorization. And since you know that the numerator of this is irreducible over the integers, meaning it has no integer solutions or rational solutions for that matter, you start looking around for a way to rearrange these factors to where you get consecutive integers, being mindful of this minus sign right here. Okay. Now the rearrangement, a lot of you may have already spotted it. It just steal a 2 away from here, and you have 2 cubed, right? We'll leave 3 squared intact because that is also 8, right? That's 8. So this is 8, this is 9. It looks consecutive to me. Now right here you have 2. Take one of these 2's over here and hook it up with the 5, and you have 10. Right? And then you have 7. So you see what you have here, folks, is 7, 8, 9, 10. 7, 8, 9, 10. And the only way to get a 7 right here and keep things consecutive is to take, in other words, make this negative 7 here. So y'all, we do have a minus sign here, but we need it, and whatever, if we choose a minus for our x, everything's going to cancel out nicely. What's this right here? Minus 8. So we have consecutive integers, namely negative integers. What's this, negative 9? And negative 10. This is very cool, I think. And I'm surprised that math resource on the web wouldn't notice that. But that certainly implies that x has to equal to negative 11. Let me get that circled. So it turns a problem that would have been difficult. Again, if you multiply this out, you would get a fifth degree equation, right? And you'd have an enormous constant. And again, I didn't give that hint to that there is an integer solution, so that's a big deal. And it's unclear if I would have known. I mean, I don't think I would have known to try this idea here had I not been aware of the fact that there is an integer solution to this constructed, designed to work equation. Okay, so x equals minus 11 is a solution. No checking is required here. Right, just because of the fact that the numerator is irreducible, 13 can't be involved in any way. You have to, the 13 is inert, so to speak. And this would be the only, now I haven't proven that really, but this is the only consecutive integer arrangement you're going to get out of this prime factorization. And again, again, a lot of hand waving there. It's kind of tedious to say that's the only one, but it's pretty clear that this is the only solution based on rearrangements of these prime factors over here. Okay, folks, that is all. T-Rex approves, I think. He just nodded.